Oh, today we're starting pretty late, so I'll keep this as short as possible. So I wanted to give an introduction to rocketry and how to build rockets. So let's look at some designs. So all rockets share.
Can you
What do you want me to do?
use the computer?
He thinks that you're talking to him.
Yeah, please go ahead. I can share it connected.
Okay. Um, so all rockets can be broken down into two primary sections. We can call these the three primary sections. We can call these the payload section, the nose cone section, and the booster section. And you can see designs of these below. So this booster is where you house the motor, and many modern rockets, like the ones you probably see in images, are the big liquid propulsion systems. These use gases such as hydrogen and oxygen. And when these molecules burn, Newton's third law, equal and opposite reactions, causes it to push the rocket upward. Um, and these rockets reach exit velocity and they end up going to space. However, you can see that the booster here is quite small compared to the rest of the rocket. That's because this isn't a liquid propulsion rocket. As these rockets, the boosters and the motors tend to take up 80% of the overall length of the rocket. And as you can see, this one is much. This is a model rocket, so you can think of it as a scaled down rocket. So this is what they use to test everything that they need to before they go up and launch the bigger rockets. So in these rockets, the booster or the motor section that powers the rocket is around 30 to 40% rather than around 80%. And the main reason for this is that it just uses propellants, so gunpowder, a gun, what you could call a gunpowder, but really it's a more sophisticated mixture of chemicals. And when lighted, these give you propulsion, but not to the same extent. So, for example, if you want to use something like this, you couldn't go to space just because you wouldn't have enough power. And then payload. So we're not launching rockets just for fun. They're designed for a purpose. So in this case, a payload can store something that we want to do with it. So for example, when those big rockets go up to space, they can carry humans or they can carry technology. However, in these smaller model rockets, sorry, let me get to the slide. There's something you want to get done. So maybe there's an experiment that you want to do, and the conditions that come from being in a rocket, you get high G forces, which is the force from gravity as you oppose it. So when a rocket flies up, you're opposing its acceleration by accelerating an object upward. Therefore, it has a G force. And these are high G force environments between 4 to 5 Gs. So within those environments, you can conduct experiments. So when you see those big rockets go up into space, they oftentimes are have humans in it. Whoever that is, may mute themselves. Okay, yeah. So, um, so in smaller rockets, you can conduct experiments like this. So in this one, I think I have a better picture. Yeah. So in this experiment, for example, um, so sound when I speak, that's molecules in the air vibrating. That's how you can hear what I'm saying. So in this experiment, we wanted to see the shift that occurred from this top speaker on your very left to the bottom speaker on the very right, and there's a microphone in the middle. So in theory, if you launched a rocket such as this one, and these speakers were playing, they would play the same sound, but this one would actually sound a little different. The top one would sound a little different to the one on the bottom, because of course a rocket can approach the speed of sound, and as something approaches the speed of sound, the frequency changes, and with that frequency change, you also get the sound changes as well, because it starts to bend the rocket starts to bend the air around. So with payloads like this, you can do much more complex things on the ground, things that don't require you to go to space, but you still need the high G-force, high acceleration environments that can only come from being in a rocket. And I guess we can take a look at a couple more payloads. So this one, as you can see, is an electronic payload. So on the right image, there's a ball, and in between it are these actuators. So these emit sound, and during flight, this ball can levitate. So another thing you can do with these model rockets is, rather than just researching something, you have a problem like before, or you have an idea like before about the shift in sound. Here, you can experiment on you can get this little ball to float. So basically it'll just, once you turn these on, that little ball will just float in the air. And essentially what we were trying to do here is we were trying to get it to float throughout a rocket's phase. And then you might be wondering, why would we do this? What are the implications? Well, when astronauts go to space, they float around because there's no gravity. There's nothing acting on them, pulling them towards the ground. So with things like this, you could theoretically make an artificial gravity where astronauts and people who go to space, they can actually stand and walk just like they're on the planet Earth. And then this one was simpler. So sometimes you'll see images of like rovers, these little vehicles that will go on the surface of another planet. So this was kind of like that. So essentially the rocket goes up and it deploys this, and as it comes down, it takes images and a video of its descent. And again, what are the implications of this? Well, when you see those big rockets go up, and they'll have something like this in their payload. And as it comes down, you can see other planets, what other planets look like, what their atmospheric compositions are. So this is really just a scaled down model of what a rocket does, or what it looks like. Someone said they could not hear me. Can everyone hear me?
Yes, like me, I'm able to hear you.
Okay. So yeah, this meeting went on late and we had some trouble, but so I wanted to go more in depth, but I know that this meeting probably ran on longer than both me and all of you were thinking. So there's some other stuff I could talk about, such as stability and how you can actually make rockets like this, and just general rocketry stuff, and delve more into the physics of rocketry. But yeah, this meeting ran a little longer than I think we were both thinking, so I think I'll just hold off on that for now. And right now I can just get any general questions you might have that I might be able to answer. So does anyone have any questions that they want me to answer? Okay, if not, I guess we can end this meeting. Again, sorry I wasn't able to give you a lot more information, but in the following next time I see you, I'll give you a lot more information, and we'll delve more into the mathematics and science of rockets rather than just a general overview. All right. Thank you. Bye.
Much.
Peace.